I want to briefly touch upon the other topic, okay? This all-path minimum phase decomposition. And we'll continue this discussion on Thursday, all right? So now the new topic is there are quite a system that is called the minimum phase. Minimum phase system. And the concept that we can always decompose the causal and stable system into all paths multiplied by minimum phase. They multiply in their system functions. Okay, so let's touch on the definition for now. We'll continue the discussion on Thursday. Okay? Definition. What is a minimum phase system? Okay, this is a terminology. Okay? A minimum phase system is a kind of system whose poles and zeros are all inside the unit circle. All the poles and all the zeros are all inside the unit circle. If a system has that property, then we call this system a minimum phase system. Very simple, right? Definition, let me just draw a picture. If we have a unit circle here, with radius 1, and if we have a system, a difference equation system, okay, and we can always write down the system function. And when we build, and if the system has all the zeros, if all the zeros and poles are inside the unit circle, not only the poles, but also the zeros. Okay? Okay, so if all the zeros and poles are inside the unit circle, then we call this system a minimum phase system. Minimum phase. So let's say a minimum phase system has all these poles and zeros inside the unit circle. And let me just describe inside the unit circle. You know what I mean? Okay? So that's simply a definition. Okay, so if I give you this definition, there must be a reason why we want to talk about it. Okay? So we just share with you that what is the advantage, what is the cool property of this system. If a system has all the poles and zeros inside the unit circle, then we say that the system can be inverted. Then the system has a causal and stable inverse. Let me say that again. If a system is a minimum phase system, then this system has a causal and stable inverse. Causal and stable inverse. By inverse, I mean that here's the thing. The input and output is going to be, the input can be recovered if you receive the output. Okay? But let me first write down that statement. A minimum phase system has a causal and stable inverse. That's the statement. Or should I say a cool property? It is cool. A minimum phase system has a causal and stable inverse. So for this, I mean, let's say if the system is H, or just say H of Z, okay? Better. If this system has a system function H of Z, input X, output 1. And if we know that all the poles and zeros are inside the unit circle, then we can construct a system, let me say is G of Z, such that we recover the input received by receiving the output. Okay? So the input can be recovered after we receive the output. And in this regard, the recovering system G of Z, so the question is, what should the relation between G and HB? What is that relation like? What is the requirement for us to recover X by receiving Y? The answer is simple. Let's define G of Z as 1 over H of Z, right? Very, very simple. Okay? If G of Z is defined as 1 over H of Z, then the overall system here, this system in combination, H followed by G, then the overall system function exactly should be H of overall. The overall system function should be just simply H of Z times 1 divided by G of Z, which is 1. Right, that's done. That means if we put this G of Z after H of Z, then in principle, we can recover X whenever we receive Y. Okay? So this is what I mean by inverse. Yes? I'm sorry? Oh, yeah. Thank you. 1 over H. Thank you. Any other comments? So in principle, whenever we have H of Z, you can always try putting a G of Z. Right? So if H of Z, for example, if H of Z is BZ divided by AZ, as usual, then we can always try requiring G of Z to be AZ divided by BZ. And in principle, then the product of H and G should be 1, right? So in principle, this is the simple idea. We try to construct an inverse system so as to recover X input. Okay? But the question is, yeah, you can always, for any BZ divided by AZ, you can always write the inverse, AZ divided by BZ. But the question, that new system might not be stable in general. Okay, so let's say if HZ is stable, a stable system might not have a stable inverse. That's the problem. Okay, so for any given system, even if HZ itself is stable, it may not have a stable inverse. And what conditions can we make sure that H has a stable inverse? So that's why we have to require the zeros to be also located inside the unit circle. And what are zeros? Zeros are the group of B of Z. Okay? So if we require both the pole and the zero to be all inside the unit circle, and for that kind of system H, then we can be sure that when we just change the position of A and B, the inverse system G is also stable. Why? Because all the groups of B and Z are inside the unit circle. Okay? So that's why we say when the conclusion is this minimum phase system, by definition, the definition is that all the zeros and poles are inside the unit circle. And for this kind of system, it has a cool property that the inverse can be also called unstable because now all the zero and poles are inside. When zero becomes a pole, the pole becomes a zero, they are still inside the unit circle. Okay, so that's why the inverse of this, we can construct a stable, called a stable inverse for any minimum phase system. That's a property. Nice property. Any question? Well, you might wonder, what is the application? What is the application when we want to construct an inverse of a system? What are the applications? There are quite a few. Have you ever sent somebody a document by fax? You say it's something good. Have you ever sent a document to somebody by fax? Come on. You're not that old, right? You've seen fax, right? Are you still using a fax? You have a fax at home. You still do? But in any office, so you find a fax machine, right? Have you ever wondered, whenever you send a document to somebody using a fax, what happens at first, before the connection is made? What? Scanning, before scanning. But have you noticed that typically you see the machine making noise? Like beep, 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 beep. Right? That's right. Have you ever wondered what is that about? The system, because fax is to send a document, they teach you the document over the phone line. That's what fax is, right? So over the phone line, because there's always some channel distortion. The frequency response is uncertain. The dialing, you're sending a document over the phone, the network to someone. So the frequency response of this channel is uncertain. So the fax machine at that time is performing what we call a system identification. It's trying to identify the system. It's trying to estimate the channel distortion due to in between the transmitter and receiver. It's trying to estimate that system function by known signal. It's sending a big that's a known signal. Okay? And then it's sending the signal, and also because it's phone line, it can also record the signal. And then after doing that, it can be sure what kind of HFZ we have. And once we have done HFZ, we can try to invert. You can try to invert it. We can try to undo the channel distortion as best as we can. So that's why the fax machine is performing system identification, because the channel is distorted. Okay? So you still have that after the sound suggests, okay, HFZ has all the zeros inside the loops. And that's good news, because we can construct a causal and stable inverse so that the combined system will have no distortion. Okay, so instead of sending X, we can send GX. Okay, so instead of sending X with Z, let's try to send GH. Let's try to digitally process X before sending. And in the end, we can be sure that Y will be equal to, Y of Z will be equal to H of Z times G X, and that's exactly X. So we have perfect transmission. Okay, so that's why it's important to talk about whether or not the system can be causally and stably inverted. And it has a real application. Okay? So I want to share with you, that's all I want to talk about.